So, as the thumbnail already says, this lecture is about introduction to the vector calculus, and in this lecture, I'm gonna talk about some topics like scalar field, scalar field, and vector field. We're gonna discuss about these topics, and then the third topic will be differentiation of scalar and vector fields. So these three topics I'm gonna cover. So I'm gonna start with a scalar field, and how will I define it? So scalar field, scalar field. So scalar field is a function of spatial coordinates and it returns a value. So I'm gonna say it like this. This is a function of some x1, x2, dash xn. Okay, and it returns a value, a single value. These all are spatial coordinates. Okay, and this is a single value and it can represent a physical quantity. Okay, so scalar field is a function which associate every point in space to a physical quantity. Suppose a function of xyz, and what it gives temperature. So it associate all these points to a value of temperature. This can be a scalar field, and we can also represent it as a scalar field of temperature like this. And another examples can be potential. Potential is a function of position and it gives a value at that point. So these all are the example of scalar field. And the thing is, this is scalar. Why the name scalar? Because it returns a scalar value. This is a scalar. Okay, it takes scalar. The domain is a scalar and the range is also scalar. So this is a scalar field. The name is a scalar field. Next is vector field. So vector field is also a function of space points like this, and it gives us a single value. Okay, but this time this function is a vector quantity. Suppose electric field. Electric field can be dependent on space points, and every point in space will be associated with a value of this scalar field. So this value is the magnitude of vector field at that point. Okay, and each point will have a direction of this electric field. So suppose we have this coordinate system and our vector field is like x comma y, and let's include this also. So if this is x, this is y, this is z. So every point, suppose this is x, y, z, and suppose this is the direction of electric field. So like this point will have some different value and different direction. So like this we can represent vector field. So in a summary, if I summarize all this, scalar field is a function, scalar function of space points. vector field is a vector function. It is just like scalar field, but it will also associate a direction to that point. Okay, and it's not like every function of xyz can be called scalar field. The function must be continuous. It must be continuous and differentiable. Differentiable at every point. Okay, so our third topic was differentiation of scalar and vector field. So we already know about differentiation. Okay, we have already worked on scalar field of single variable. I mean a scalar field like some function of one variable only. So this is also a scalar field because it contains a space coordinate, and it will return us a value. So this can also be characterized as a scalar field, and we know how to define the differentiation of it. So differentiation, which is denoted like this, is limit delta x tends to 0 fx plus delta x minus fx divided by delta x. We can define differentiation of this function like this. But what about derivatives of functions having more than one variable? Any differentiation of multivariable? Differentiation of multivariable functions, or I will call them scalar field here. Okay, so for that we use symbol like we have a function of x and y, and the derivatives of this function can be denoted as del x f, del f y, del f by del y, and double derivatives can be represented as del 2f, del x, del 2f, del y, like this. And one more derivative can be written as del x, del y, or they may not be equal, but if the function is continuous and differentiable everywhere, these two are same. So how we will define these? So for that, suppose we are finding this, and this is defined as limit delta x tends to 0 f of some x plus delta x comma y. Yani we have incremented only x coordinate only. This is so this is defined as this is also known as partial derivative. Yes, partial derivative of f. Okay, the same way we can define del f by del y, like limit delta y tends to 0 fx. This time we have to increment or decrement y plus del y minus fx comma y delta y. So this becomes, and same way we can define higher derivatives of it. What about this? So this is nothing but you can split it like this. So first you find this which is already defined like this, and then you also change the x variable, keeping the y variable same, constant. So what this means, if I define them, this is change in f when x constant, and this is change in f when y is constant. And we have treated x and y constant when calculating the change in f. Okay, so we have talked about derivatives of scalar field. The same way we can also define also define vector field derivatives. So suppose f is a vector field this time, and I will write it simply like this, and we know this is a vector field of x and y coordinates. So for this I can write del f upon del y. Nothing gonna change, the definition will remain same. Delta y tends to 0, f of x comma y plus del y minus f x comma y, like this, and divide. Okay, but this time this gonna be a vector quantity. So until now we talked about let I summarize here again so I don't miss any topic. We have talked about a scalar field, we have talked about a vector field, ये हो गया. Second, we have talked about differentiation of scalar and vector field.